Hello, today I'm going to report on the block diagram representation of control systems. Control systems play a crucial role in automation, robotics, aerospace, industrial processes, and many other domains. To analyze and design control systems efficiently, engineers use block diagrams, which provide a graphical representation of the system's functional elements and their interactions. A block diagram is a schematic representation of a control system that uses blocks to represent different components and arrows to show the flow of the signals. It simplifies complex control systems by visually organizing components such as sensors, controllers, actuators, and feedback mechanisms. So what are components of a block diagram? Here, one component is blocks. It represents system components such as controllers, plant models, or filters. It's denoted as rectangular boxes with input and output signals. So right here is a blocks. Another one is a summing points, or this one, which indicate the summation or subtraction of input signals. It's represented by a small circle with input arrows labeled with positive or negative signs. Branching points, this one, points where a signal splits into multiple paths to be processed by different components. Arrows and signals. So it indicates the direction of the signal flow within the system. So here we can see arrow here, arrow here. So it indicates the flow of the signal. And lastly, the transfer functions. So it represents the relationship between input and output of a system component using a mathematical equation. So here, to simplify some of the blocks, this one here could be replaced by a transfer function contained in a block. So representation of a control system using a block diagram. So the notation for block diagram representation is as follows. For the reference input, it's called the R, noted by the R as a function of S. Here is an example of an R. It's the desired output or set point. Controller G. So it's a processes to the arrow signal to generate control action. Another plant process G underscore P, or the plant, the system to be controlled. So as you notice, there's a lot of G's here. It's all a block, but it's noted as G underscore S for the controller and G underscore P for the plant or processes. Sensor or feedback noted by H as a function of S. So measures the output and sends feedback. So here as an example is an H. Summing junction computes the error signal as the difference between the reference input and feedback. So these here are the summing junctions. And lastly, the output C is a function of S, the system's actual output, which is this one. So in block diagram, there are reduction techniques. So this makes the block diagram simplified and in more summarized visual representation. So here are the examples. Series connection. If two blocks are in series with transfer functions multiply. For instance, if you have a series G1 and G2, the equivalent of those blocks are G1 multiplied by G2. If the blocks are parallel, then the two blocks will be added. So in this case, if you have two blocks G1 and G2, the equivalent is G1 plus G2. So an example for a feedback loop, the below equation is an example for a basic negative feedback system where a block G is divided over 1 plus G multiplied by S. And remember, S is a sensor or a feedback system. So another technique is moving summing points and branch points. It's used to reorganize the block diagram to facilitate simplification. So what are the advantages of block diagrams? So one, visualization. It provides a clear and intuitive understanding of system components. Two, simplification. Helps in reducing complex control systems into manageable representations. Three, analysis. It assists in mathematical modeling, stability analysis, and system design. And flexibility. It's easily adaptable to modifications and changes in the system components. Here, I'm going to show you a block diagram in MATLAB, and we're going to simulate it. So a knowledge of block diagram is really important. I'm going to show you how in a block diagram cases like simulation. So here's the video. Using MATLAB. So here, you can see a MATLAB example of an anti-wind-up PID control example. So let's inspect a few parameters of the block diagram. So here is the set point. There's a PID block. There's a summing junction. So if we're going to inspect the set point, it just says the initial input is 10 and the final value is 5 after a step time of 8. And if we look into the PID parameters are here, 2.7, 0.3, and 2. So I'm not going to discuss PIDs here. I'm just showing how block diagram, understanding of block diagram helps us if we're implementing it in a simulation. So if we run the simulation, and we're gonna check the scope here. So here, the set point is the one in blue. So when we check that set point, it was 10. Then after 80 steps, it drops to 5. So this part here is the output, is the actual output. So as you can see, based on the parameter set on the block diagram, it follows the set point. So by the time it drops to 5, it also follows 5. Thank you. In conclusion, block diagram representation is a fundamental tool in control system analysis and design. It enables engineers to model, analyze, and optimize control systems efficiently. By using the block diagram reduction techniques, the complexity of a large-scale system can be significantly reduced, making it easier to determine system behavior and stability. That's all, and thank you.